Lab 3, the mass of a black hole. In this lab, we will be using a computer model GlowScript to predict the unknown mass of a black hole in which a star of known mass orbits. We will be using the parallel and perpendicular components of dp/dt and relate it to our overall dp/dt and fnet. For initial conditions, we had the trajectory of the path was set random as determined from an email address. We are given that the star's initial mass to be 2.0 e to the 30th kilograms. Our time step delta t is also defined as 86,400 seconds or 1 day. A full orbit is defined as 1 year inside of our model. For initial conditions, let's begin to define our velocity, which is the change in x over the change in time, and our momentum, which is the mass times the volume. We also find the change in velocity and the change in momentum and put it in our code so that we may derive our dp/dt for the overall fnet. As you can see, it is delta p over delta t, and when we define this to be our fnet. We also defined our p hat, which is the momentum over the magnitude of the momentum, and our dmag p dt from subtracting the magnitude of the initial momentum from the magnitude of our final momentum over our change in time. Then we find our parallel dp/dt by multiplying it by our previous result times the p hat. We also defined it to be our fnet parallel, as shown in the last step. Continuing on, we find our perpendicular component of fnet by subtracting the parallel component from our overall dp/dt. We also define this as well as fnet perpendicular in the next step. We also find the mass of the black hole from deriving our formula from the only force that acts on the system being the gravitational force. We have our fnet shown below, and by isolating our mass of the black hole, we find that the magnitude of fnet times the distance squared, or times the magnitude of the distance squared over the g, the universal gravitational constant, times the mass of our star gives us the mass of our black hole. For our model in action, we begin to see our arrows, which in magenta is the parallel component. Our blue arrow is the perpendicular component, which points to the center of the trajectory of the circle. And our orange is the overall fnet, which always points at the black hole. As you can see in our second clip, the magnitude of the perpendicular and the overall fnet drastically increases as the distance between the star and the black hole decreases. And once we begin to move away, the magnitudes begin to decrease. We can also note that in our parallel component, when it is pointing in the direction of motion being counterclockwise, we see that it is increasing in speed, but when it points in the clockwise direction, it is beginning to decrease in its speed. Graphically, we can see all of our data points from our overall fnet, our parallel and perpendicular component. Our fnet, our overall fnet and perpendicular components are relatively the same in terms of their magnitude, but our parallel components, our perpendicular and fnet are relatively the same, but our parallel component is pretty much the opposite of our fnet, our overall fnet, and our perpendiculars. This is shown as in our last slide, as you can see where it differs from the direction. Conclusion. What is the difference between the net force and the rate of change of momentum and the parallel and perpendicular components? There is no difference. They both describe and define the momentum principle, as we found that dp/dt is equal to the parallel component plus the perpendicular component of momentums. What if the black hole was replaced with a new black hole and the motion of the star remains unchanged? Our code can infer this change and calculate the new data for the mass of the black hole.